Hey, Jesse. People hear me?
I heard Radley.
Okay. Yeah, I'm just testing. I didn't know if people can hear me or not.
Yeah, I can hear you. One.
Okay. I guess welcome to the meeting. I didn't know how many people were going to show up today. I had we have our Jitsi issues, and so I just wanted to make sure that people had gotten the link and everything. But so welcome to the meeting. And this is the aftermath, I guess, of NeuroMatch has ended yesterday. So congratulations to everyone. You finished the session. Anything anyone want to bring up before we start?
I would ask, is there a specific time, like, there's a bunch to say about NeuroMatch, so I don't know, like, there's a specific, is that going to be part of our discussion later, I guess?
Oh, well, yeah, I guess we'll probably talk about it a little bit. We can talk about it. Ash looks like she has something to say about it.
I'm still in a Stockholm syndrome. I just don't really get to know how I would do after Monday or something.
Yeah.
With such a very fully packed hours, and then I don't know how I'm going to do my stuff later this week.
Yeah. Well, let's see. I don't know who else is going to show up. I wanted to.
I think Edson will, but he's on his way.
Oh, okay. Yeah, I didn't want to start in on something and then. But I guess I wanted to recap some of where we are right now with things. So the first thing is that we finished NeuroMatch, and all three of you in the meeting right now we're in this group that started. Is that Anson? Yeah, there we go. Hi.
Hello.
We were in this group, except for Anson, that did the feedback loops thing. So that's the group that was formed kind of a week into the group formation. So they really didn't have a lot of time to do the data analysis in that. It was pretty challenging too. I was working with Ashk on it, and I had like two other groups that I was mentoring. One of them made the sort of the profiles in the summary. I think you saw the summary sessions, so that's good. How did your group fare, Anson?
It was a struggle. So I spent some time trying to apply hidden Markov models to it, but I didn't have prerequisite knowledge, so that I ended up deciding that it wasn't realistic in the time span. So the rest of the group was focused on applying LDA to the data, and we got some initial results, but the initial results were, we got, I think it was 40 to 50% correlations, which were great results, and we had some issues with the data, the format, with a little bit of interpretation, but mostly it was just, we spent most of our time pre-processing and trying to pre-processing the data, and it seems like it was a lot of, it was really, I'd say overall, just like neuromath, it was highly stressful but interesting. I didn't, I think, I'd say it was a good learning experience, even if our results weren't that great.
Yeah, that was the consensus, I think. I mean,
Yeah.
I think the whole point was just for people to do the project, and then that was good. I mean, it's a good experience. I like the way, for the most part, that they have the data set up, but I think it shows like a lot of the challenges of sort of reusing data sets and using data sets to answer questions. So one of the other things that we do in the lab here is work on open data questions, and so we have these data sets that were sort of made. They collected data. They tried to collect it in a more a pretty general way. Not necessarily, well, maybe to answer some questions, but to also have data for a wide range of behavioral experiments. That's why they picked the data sets that they did. And so, but even then, you have problems with getting the data organized and the quality of the data. And then one of my other groups, they had problems with matching. They had the brain was divided into parcels instead of into regions of interest. So they had to make that connection between the two units of measurement. It was a limitation, of course, but I mean, those are the kinds of things you're going to find if you use a lot of secondary data sets. And it's not it's not the fault of the people collecting the data, because they're just collecting data and they have these great data sets. But a lot of times it's hard to make it public, and it's also hard to get it to maybe to apply it to some question that it wasn't originally meant to answer. So you find these problems throughout. You just have to find ways to work around them. And sometimes they're easy, and sometimes it's pretty difficult to kind of figure out. But I think that was a good experience for everyone.
Mm-hmm. I think neuromath really highlighted the importance of, one, prerequisite knowledge, and two, it was a good overview of what exists and how it's applied, even if I couldn't grasp all the technical knowledge.
Yeah. So let's see. Today we're going to talk about. I think Jesse wanted to say something about this post, or he's going to present something on the work that we did for the A-Life abstract.
Yeah. Let me see. Actually, I probably could use my screen for this, but basically, I will be doing another summer school after this, and let me see if this can work. Not directly after, thank goodness, but I got into the Brains, Minds, and Machines summer course, which is sort of through MIT and company. Originally, it was through the Marine Biology Lab, as like the housing organization, but everything in person has just been canceled. So sort of like NeuroMatch, it's been moved to virtual version of it. However, it will NeuroMatch is you guys will have much better and more thorough training in NeuroMatch than, even though it has like a bigger name with this, like NeuroMatch is like so it's a summer school, but the virtual version of it is sort of, I'm not trying to downplay it by any means, but like it's going to be like a kind of 5 hours of lectures and some discussion, and I don't think there's going to be a project component or anything else this year. However, what they are doing from what I understand so far. And I'll try to share this. Let me see. Yeah. Okay. Here we go. Okay. All right. What they are doing is they are doing a poster session, and it looks like you can just present on topics that are. Does it say here where it is? No, I don't think it says it here. Maybe I can look at this quickly. Well, there's the opportunity to present a poster, and it's a little bit unclear because, like, I don't think this course has ever done anything, a virtual version of it either, so they're a little bit kind of behind the curve, whereas NeuroMax's maybe was like, ahead of the curve in some senses. But yeah, here's the schedule at least. And I'm still kind of talking about this with Bradley, but my idea, I just basically put my hand up and said, yes, I would like to present a poster. And what I'm going to try to do is present some of our past work, or sort of our cumulative work, I guess, on everything that we've been doing in the MetaBrains project. I guess you can see there's a virtual poster session here. I don't know which one I'm going to be at yet. I don't know if that's going to be open to the public or not. But long story short, I'm going to try to put together a poster on some of our kind of with the last up to the last 2 years in one sense, not entirely, but the MetaBrain project, and hopefully present at one of these poster sessions at the virtual event. I don't know yet. I have no idea what the details are, but I'm going to try to do something like that and see how it goes. So I basically have, I don't know, potentially a week or so to make the poster. So I'll probably talk about it in Slack, and I don't know if it's going to be open to collaboration or not, but I mean, as much as possible, I would try to do that. But.
Yeah. Well, I mean, I was just thinking we could probably come up with some, we have materials from the presentations we've done, and so that could be used if you want to.
Yeah.
And then, obviously you'd have, I don't know if they have, co-authors or, because, there's stuff that I want to credit people for. And then we'd have, but, you could use any. I know virtual poster sessions, I guess they're just kind of creating a poster from, you create this big canvas and you can put things on it, as opposed to a talk where you have to kind of put it in sequential slides. So, it's,
I actually really like that. Going back to NeuroMax for a minute, I like how there were some virtual people made some posters and kind of went through the parts of it, and it worked out really well. And I imagine that's going to be pretty much the same thing. Although I have a strong feeling that NeuroMax will be a little bit smoother flowing than whatever I get into with this other one. But yeah.
Yeah, I think they had the timing really worked out well with NeuroMatch compared to some of the other events I've been to. People are trying to do this now, or they're going online, and it's a varying success. I think people have had varying success of making things virtual. Some people have done really well, and some people maybe not.
Yeah.
But yeah, I think we'll talk about the poster. So it's like I said, and then they have these poster. You can go online and find good designs for posters, or there's a thing called Better Poster, which is a template for making posters, trying to optimize the information content, because posters are very visual, so you want to emphasize the visual elements. So, but we can talk about that in Slack more.
Yeah, that was something that obviously came up kind of quickly this week, and at least for me, everything else has just been neuromatch. So it's sort of the first morning where I'm waking up and not thinking about neuromatch. Although I'm happy to talk about it. Oh, hey,
Angela.
Hello, Angela.
Hello. You're still here now.
Oh yeah, my auntie cut it recently.
Nice. Suits you well. Sorry for cutting you off, Jesse.
no, I wasn't sure where we're going next. Actually, I don't know. If we had any more to say about neuromatch or already on to new things, because I know I feel like I've talked a lot about neuromatch, but.
Yeah, well, if anyone else wants to say something, I was going to talk about the project next, but we can talk if anyone has any comments or reflections.
Okay.
It was a fire hose. I feel drained, but also I felt drained last night. I felt drained and euphoric, which I think overall is a good thing. I definitely need to recover my energy and like just probably 1 or 2 days off and then rebuild. But I think it was a good experience. It was a good exposure to what's out there. I really enjoyed my pod and meeting the people within it. Though I've heard that I was I feel pretty lucky that pod I did. I am. I feel like it was probably the highlight of my summer. I'm mostly glad it's over because it was exhausting.
Yeah. It's usually the way fire hoses work, I guess. It just gets, takes a lot out of everyone.
Yeah, I agree with that, and I said a lot about neuromatch the last couple of weeks. So I would just say I really appreciate my pod and the TA. I think the TAs did a really great amount of stuff. Even the TAs that I tangentially interacted with in the other groups that when people left and things changed, even the adaptiveness and the willingness for people to do stuff after, things didn't, things weren't perfect to begin with, and then they didn't go perfectly at times, but people really tried to make the best of it. And I think that's great, and the content and material is great, and I'm really happy to have stuff to go back to and a forum to talk about it with, and people to just talk about it with, there's a lot of care that went into Neuromatch Academy, and I don't know yet if people realize how much, because it was made in a very short time, but it was also made to be timeless in a lot of ways, and not even just I don't know how many people here saw the conclusion portions, whatever time slot they were in, or if Bradley saw things. I think Anson saw most of stuff last night, he said. But they're looking to continue things with books and other projects and other ways to do data science and stuff, and ways to be involved and ways to make it more inclusive next time. That's great. But also, in a big picture sense, I think I'm going to write. I have, in my copious free time now, I think I'm going to finish all of my blog posts that I've been making, or small commentary reflection articles on iClear and the other stuff that I mentioned earlier, and did a big presentation on. And I even want to do one about Princeton and Vision, which a couple of people here have been to actually, because I've drafted this one about how to Princeton and Vision, and also what's this? No, I haven't heard of that.
Oh yeah, I was going to bring that up. So Bob, yeah.
So as he mentioned about that MIT course, I was also planning to join another. This one is also done this year online, and it's about neuromorphic engineering, which I also got introduced to it quite recently. As I have been told, it's the hardware component of neural networks and stuff like that. So like just as a just I'm just putting it out there that it's like the registrations are still open, and again it's just a bunch of lectures for 5 days, and then there is also a project, and there's a 1 month timeline to it. So
Yeah, hope to hear more about that as you do. Is it start soon or?
yeah, it starts Monday. It starts day after tomorrow.
Okay. Well, if we could.
But the registrations are still open as far as I know.
Okay.
There's a Slack channel where people like most of the people are highly qualified. Like most of them are PhDs and stuff in specific to this thing. But just as a exercise to myself as was in NeuroMatch Academy,
Yeah, and that's something that like the common theme about potentially that and NeuroMatch Academy and Princeton and Vision, especially those three, getting exposure is so important, and I think everybody here is kind of understands that and is like willing to do that. But like it's just, even if you're not like it's perfectly fine to tour things as much as you can and get exposure, because especially in the field, like personally speaking, in this field, I've been like the frontier of all this stuff, of like cognitive stuff or neuroscience or mind or brain. Like there's just so many different directions and ways to look at stuff and get involved that it's really important to put yourself in positions to learn more and talk to the people who, because there's just no way you can even conceptualize a lot of the specifics of some of the fields. So you kind of have to just talk to people and see what they're doing, and these things are great for that. And that was kind of like that, plus the NeuroMatch Academy blog post or idea, and if people are interested in writing that, we can talk about that later too, like if they want to participate or something like that. But one of the things in it I specifically want to say, or we'll do separately, is like NeuroMatch Academy is like I don't think it's a stretch to say it is historical. It is making history. It is doing something amazing in 2020 like that hasn't really been done before to this level. And it's specific to neuroscience and doing computational science things with neuroscience data. But I think it opens the door for a lot of education, a lot of computational focused education as well. But just like it's a very special and important, kind of defiant, I think, in a positive way, action that took place against the backdrop of 2020. So I
think initially we planned it out as like a replacement to the original summer schools, right? But I think now they'll continue it online. So would that affect the original summer schools these people had, Cosmos and stuff?
To be determined, but I think the NeuroMatch impact is quite remarkable, I guess.
Yeah.
So, Ash, did you have any comments about NeuroMatch? Any reflections? But Angela, I don't know if Angela was in NeuroMatch or not.
I wasn't actually. I was going to do the observer track, and then I heard some like horror stories about how it's a fire hose, and I just focused on my own classes that were actually graded.
Okay, yeah, that is.
Well, I don't think. I think that's a bit of a misnomer about the observer track, in that you didn't. There was like no obligation. Like there was no. It was a lot of information, but like it wasn't oppressive. I mean, other people could speak to that who were in it. But what was oppressive was the intensive track.
Like I don't think observer track even like did mean anything except for taking initiative. Like all the content was available online anyway, and like the only thing that they did for the observer people was connect them to core, like make like a pseudopod kind of thing, and most people observed that pod do not respond, like
Okay.
like to a bunch of inactive people.
I see. That makes sense.
I was on the observer track and I was connected to 4 people. We exchanged less than 10 emails and then like there was nothing. That's about it. So it was just an introduction and like no real project was happening. Nobody was checking your progress or anything.
Yeah, and that's totally fine. But just don't. I would just say that to anybody who's like, "Oh, I don't want to sign up for Observer Track next time," or whatever. Like, I mean, that kind of leads to a broader discussion. To finish my point, like Observer Track isn't. You can do that, or you can look back on the stuff. Like, even frankly, I think pretty much everybody's in the Observer Track now, in the sense of you can just go back and look at the material and post in the forum, and that's pretty much a similar experience that you have with a little bit less, guidance. So, but also like, I think, I know I mentioned this in my past videos, and I don't want to dwell on it anymore, but I do want to say, like, I think one of the things they can do, and I noted because in their final survey, they're very aware of things, but I think there's a little bit of room to improve how, like, the worst part of it depends greatly on who's in the pod and how things are going, but the worst part of the experience for me was situations, and seeing other people and hearing other people in these situations where it was essentially a rich get richer situation in small groups.
That makes sense.
Because it's like, in an ideal situation, yes, you can throw together 4 people or 8 people with a TA, and there'll just be a good pacing where everybody's there. But what happens sometimes is people with very different like patience or experience levels get going, and then it gets to the point where it's like, okay, well, you have this disparity, and the people who want to go fast are going to go fast, and it's just not going to be the case where people who are young and experienced are going to say, hey guys, I'd like to go over this more, I'll slow down, whatever. It's like, that's not how it works, especially when you have people who so I think like that's something that, like, I don't blame the TAs, I don't blame Neuromatch Academy, but I feel like that was kind of an oversight where, in a normal summer school where your TAs, like, you're all in the same room but you'll be working on different projects, like, and you're all in the same thing together. I think that's the sort of the biggest crack to slip through in it. But it's very different. Like, that's very different to like actual working in the group project with other people. And like, even in my experience, we had a very disjointed, well, we mostly interacted in Slack, and we did a pretty good job for that. So I commend everybody. We're like total, like, they're very different parts of the world trying to make things happen, and that, that was good. But even in my other experiences or what I've heard, like, the group projects themselves were great to have different levels of experience because you're all constructing stuff. But I just feel like the tutorial sessions where we're going through stuff, frankly, to be very honest, like, certain days are just at the end of it, I just stopped. I didn't use the tutorial time for anything other than showing up because it just was not functional. And that's not anybody's, that's not like a problem, it's just, I think it can be easily ironed out in the future. And I think that's a very separate issue from, the pacing's really fast. Like
that makes sense.
The pacing was very fast. There was a fire hose, but having people on the same page and having like more guidance from the TAs about how to do that, I think there's room for improvement there.
It's basically the opposite of No Child Left Behind.
Meaning what?
Okay.
But then again, which one of the groupings would be better? Like, would you want a group to have different levels all scattered up, or just each group should have people of the same level. It harms at a certain place, and it.
I don't think it's about the level, and I think that's what people didn't really to get. I don't think it's about the level at all in the tutorials. I think it's about setting a pace that everybody agrees to and is maintained, because there was discussion about it, but it wasn't really maintained, and over time you just saw people get tired of talking about it. Like the people who wanted to go slower just didn't want to keep saying, I want to go slower, I want to go slower, and the TA did not necessarily enact it, and the groups kept mixing up the groups all the time, which is kind of weird, but like after a while I just didn't want to keep saying, oh yeah, we talked specifically about having a slower paced group, and it just didn't happen, or just like, I don't know what happened, and over time it's like, look, I've got stuff to learn and stuff to do, and I don't want to keep talking about this pacing issue. So I don't think it's about experience at all. I think it's about clear designation of this is the pace I want to go, or like things like that. It was more what it's about.
Yeah.
That makes sense.
Were you saying something about No Child Left Behind?
Oh yeah. So I believe that's like a law for Florida schools in which, well, I meant it more as in like they didn't agree on the pacing and didn't maintain it, as you said, but really it's that usually the people who are like pushy about having things be faster instead of making sure everyone's on the same page first. Like that's a pretty common scenario, and I wish there's like some way they can group it into like not levels as much as like deciding on pace, like you said, because I think I would have been one of the people who would have like ended up just like obsessively rushing through it, although it sounds like either way it was one of those experiences. But I do wish there was more of a let's make sure everyone understands it first and then move on type of.
Well, yeah, and it's tough because I think it got to a place where the material was like that's why I think it's important. It's a really tough thing to communicate, because people, you know, I posted about this in NeuroStars, and some people pretty much got it. Some people were like, oh, well, that's just, you know, reality. You have to show up, and it's hard to work with other people. And it's like, yes, but that's not actually what I'm talking about, in the sense of, like, if you want a specific, there's no way, this isn't the issue can be easily conflated with, holy crap, there's a bunch of material, I'm not going to learn this, I'm not qualified. Like
yeah, you didn't sign up for this. Like,
right.
Yeah. That's why it doesn't count as the same thing.
Right, but like at this, but the pace of the material, it like there's the pace of the material, which I really enjoyed, frankly. The tutorial content was great for me. I had no issues with that. Even I wish I had a little more time. Okay, but like the material, what was there on its own was just fine. It was just the dynamics in the specific small group discussions were just really sporadic, and it just entirely depended on who was there. And there was communication about things, but it just wasn't really effective communication, and it just felt, I feel like after a while people just resigned to like, okay, I'm either gonna just, you know, it just got to a situation where, you know, it's like, okay, what's your goal? Are you here to show up to look good and say you're doing stuff and like fill out the code? And it's like, oh, well, I think this is what it means. Just make your participation and move on. Are you bored because you did a summer school in this before, or are you, you know, just sort of like tuning out as much as you can because you are you know, in just not into that or into whatever, or are you actually somewhere in between that's holding like a legitimate pace? Like those were the four options that came out. And I don't want to, we don't need to talk about this anymore. But like just because it came up again, that's sort of what happened. And I just feel like that's not.
Yeah, not the same as the course itself.
I think, yeah, and I think that there's ways that can be carefully improved or mitigated. So it's not a thing to fuss about another time.
Ash, I think, did you have anything you wanted to mention before we move on?
Not really.
Okay. All right, good. Yeah, let's talk about the project. This is the one that Ash and Bavik and Jesse were involved with. So I thought that was a very good. It came together very well. I mean, we didn't get into the data analysis, but like I said, it was about a week. It was formed about a week into the projects, and the project period was rather short. But let me share my screen. So if we're interested in moving on this anymore further, we have a bunch of things in the. Can you see my screen?
Mm-hmm.
Okay, so we have everything up in GitHub. So I think it was Jesse who was involved in putting together a lot of the writing, the write-up for the description, and then I think Bavik and a few others were involved in posing the questions and getting that organized. And then I was working with Ashk on the data set. And so the data set is now available to get data out of. And so we can actually test some of these ideas. So the complexity of feedback loops, let's see. So I don't know, I can't remember. I don't think, this is the notebook with the data in it here, IBL downloading, data loading. If you run this, you end up, the data gets saved in a folder when you open up Colab, and then it can be reloaded into another notebook or into the same notebook, whatever you want, whatever variables you want to test. This is, I don't know if we have the final version of the final version of the slides up here. I don't think they are, but this is the one that I presented last week. So these slides were then taken as inspiration for the project description, and I think there's been a lot of work on that in terms of kind of thinking about how these variables might be used. So I mean, there's a lot there in terms of moving to a next step on this. If people are interested in doing that, we were working on Slack. I got a lot of Slack messages, so I was trying to keep up with them. But yeah, we can continue on with the project if people think they want to do some analysis or something. We have everything in place now.
Yeah, thanks for doing the work on the data. I haven't really gotten to look at the latest things yet. I would probably flesh out a few things just to have a bit more. I'm interested in the topics in general, but I'm curious what can be done with, especially since we kind of can at least have. I think we're poised to do some things with it, so I'm looking forward to that.
I mean, today it's like everyone's in a refractory period, but like next week maybe we can talk more about like what to do. I just, I think it's probably, and it's up to everyone involved in the project how they want to do this, but they're definitely, I think it's promising to move forward on it. Just have to figure out how. No, we don't have the time constraints of NeuroMatch. It would be.
Mm.
Ash looks like she's going to say something, or she's got her camera on. The connection sometimes isn't great on Jitsi.
Oh yeah, the screen is frozen a little bit, it seems.
Well, yeah, so I mean, we can talk about that offline if people want. But I think it's all ready to go. So I wanted to talk about a couple other things. Let's see. I was going to talk about something last week and I didn't get a chance to talk about it, but it's related to something that happened in NeuroMatch. So this is a Twitter thread that happened on, let's see if I have the whole thing here. I can't remember where it started, but it's basically this idea of so this is like an idea about how to define intelligence. So I can't remember where this starts. It's one of these. I mean, this is basically, and I have this in a folder if people want to look at this. It was a thread where they were talking about defining intelligence, and it was kind of a spin-off of the NeuroMatch. I think it was a Cording Lab discussion, and then it spun off from there. A bunch of people answered. And there's some really good answers in here. So one of them is the core of intelligence is minimizing resource expenditure to acquire necessary survival resources. Only self-survival systems must manipulate the environment to continue to survive. And then, so this is sort of a rumination on that. Then there's another take that's involves, using some version of XOR, which is a logic gate, which is exclusive OR. So some version of XOR would make sense, ideally in a flexible way, not just tested in a prescribed format. This is the person who started the post. Thanks. We're considering more general sameness differentness tests, which would involve the variance of XOR. Then someone mentioned a reasonable distinction could be biological adaptation and culturally based adaptation. Technically, the organism should be able to adapt to varied situations in the physical and cultural milieu, aka crystallized in fluid intelligence. And so that's another take. This one is like a Turing test. So flipping this around, we often use Turing tests in the simulation community to assess whether simulated outcome loops is enough like the system being modeled. This involves asking a human if they can tell the difference between simulated data and real data. Similar to your goal. This one is assimilation and accommodation. Adaptation can be usefully broken down to the Piaget-inspired aspect of assimilation. An organism adapts to fit their environment. And accommodation, an organism adapts to the environment to fit in. And then there's this one about, compositional creativity. Intelligence. To see what everyone else sees and think what no one else has thought. It's a quote. Formalizing this would be interesting. Something like compositional creation of exponentially many novel action plans that maximize reward over long time horizons of limited training experience. And then there's a perception of relativistic groupings. That is, all right, AI and CogSci folks. Oh, this is, I think, the original post. I am working on a fundamental revision of the Turing test focused on biological intelligence. What do you think are the fundamental principles of intelligent behavior? Primary computational goals, not specific behaviors. So yet another answer to this was 1A categorical perception, 1B relativistic grouping of entities, in-group, out-of-group, reduce energy usage, sensory motor interaction, predicting estimating future sensation, self-other perception. So the reason I bring these up is because they're sort of give a good idea of how people are thinking about intelligence if you survey people in the community or in the world. This is another one where they talk about theory of mind in terms of intelligence. So intelligence might be measured using a theory of mind approach. Communication is a cooperative game with hidden information. To play that game well, you need theory of mind. Also, you need to be able to model agents you have not interacted with before. So there are all these opinions about what intelligence is. I think one of the key things about this thread is that it seems like people are coming at it from a great many perspectives, and it seems like you can take what you want and apply it to your system. But of course, when we talk about intelligence, it's so broad that theory might make sense in some cases, but not others. And there are a lot of different ways you can view intelligence that sometimes it may not even make sense to say intelligence is a single thing, right? I mean, it could be that.
Yeah.
So
Well, I would definitely agree to that. Like a different, it's intelligence at uh, different levels and different levels of complexity. I think would exhibit very different things. Like one of the images said something like minimizing. What was it about? Like minimizing information, like we're basically like filtering information like for survival purposes. And I feel like at at what level, like that means someone that even if you hold that to be the case, like at that level, that's so. At looking at that aspect of things across different levels of or like amounts of complexity is huge. A very interesting lens, but would entail so many different things.
Yeah.
Which is good. So this that started from someone making a thread about a new Turing test and what would involve in it.
Yeah, I think that was the idea. They wanted to survey people. I'm just putting the link in the chat here for if you want to look at it further. But yeah, they were just surveying people. They wanted to know. They were doing this sort of Turing test of intelligence, and they wanted to know. Which a Turing test, of course, is something in computing where they look at like the halting behavior of a program. So it's not like made for intelligence. It's an analog of that applied to intelligence. So you can see right away that there's kind of an issue with application domain, but basically to say whether something is, and I guess in the case of the Turing test, I mean if something is genuine or if it's just being generated randomly. If like if I'm talking to you right now, if I'm actually thinking about the words I'm producing instead of just generating words. If you go up to like a drive-through and the speaker starts talking to you, do you know that there's a human on the other end, or is it a artificial intelligence? Yeah. So I mean that's the idea, and so we actually this came up during the Artificial Life conference. They were asking about like they have this thing about Turing tests. There was something called a fake life competition that they ran I think last year. And it was like if you look at like a behavior of some digital organism or some like simulated organism, and you see it moving or you see it behaving in some way, is it life? Is it life or is it fake? And people have taken like images of like camera images of like microorganisms and compared them with like simulated organisms and tried to like detect whether it was fake or real. So that's the idea. It's the same kind of thing where you have this thing going on and it's generating this behavior, and you have to figure out whether it's real or fake, or if it's intentional or not. And so a great many takes on that. If you have thoughts, we can talk about it in Slack. But it's a pretty philosophical thing. But anyways, so I'm gonna actually move on. So the last thing I want to do today, and if you have to leave early, it's okay. But I'm going to do a talk on agent-based modeling. It's going to be about 25 minutes. So, hopefully this is something that'll be interesting to. I think Jesse has been interested in this. Anson's been interested in this, but I hope the rest of you find it interesting. So I wondered if Ash, if she wanted to talk one more, if she wanted to try to give some comments one more time.
This is kind of new to me, like the engineering aspect of the intelligence as such, and I'm just kind of trying to follow you guys. Like, I'm listening and grasping things as such.
Yeah, I think you did a good job working with the data. We were working together on that, and I think you did a pretty good job. I know you're pretty new to Python and that, but that's the experience that you should be trying to build. It's a good. You have to get your hands dirty in the with some real examples. So that's good. Well, thanks for that. So yeah, again, if we want to talk about this more, we can talk about it in Slack, but or anything in the meeting today. But let's go on to the agent-based modeling talk. So yeah, and this is going to be
really quickly, and I'll be right back.
Yeah. So this is going to be like an introductory talk. I'm not. I try to make it pretty easy to follow along, pretty visual. So let me share my screen. Hopefully this works. So can you see my screen?
Yes, all the cells have been run. All the preceding cells have been run. It looks like it's loaded just fine this time.
Oh, good. Yes. All right. Because last time it was just kind of a blank screen.
Oh, okay, good. Okay.
Yeah, there we go. And again, I mean, this front end here is actually everything to do with agent-based modeling, unlike last week. So this is a city simulation, the grid simulation on the right, which is a more traditional version, and then the human crowd dynamics, which is in the lower left, and we'll talk about all those things. Okay, so we start out, and this is a little bit disconnected from maybe what we think about in modern day agent-based dynamics or agent-based models. But we have to go all the way back to von Neumann, and von Neumann was interested in automata. He's interested in a lot of things, but one of the things he came up with was this idea of an automata. And an automata is a machine or a computational machine that does, it basically manipulates bits or symbols, and it transforms them, and it's this autonomous thing that changes over time. And so you can see here he came up with something called a 1D cellular automata. So this cellular automata works the following way. You have this string of numbers 0 to 1 in generation 0, and then each cell has an interaction rule. So each cell or box has an interaction rule with its neighbors. And so the way it works is that the cell in question interacts with its neighbors. It observes its state, and if the state of its neighbors is 0 on either side, then in the next generation, this cell goes from 1 to 0. It basically observes its neighbors and does what its neighbors do, or a majority of its neighbors. In this case, it would be 2. If there's an ambiguity, then maybe the rule says don't change your state. Basically, the idea is you have these cells, and each cell has 2 neighbors, and you observe what each neighbor does, and then there's a rule that says either do what your neighbors are doing or don't. If it's unclear what your neighbors are doing, don't change your state. If the neighbors are the same state as you, don't change your state. But if your neighbors are of a different state, change your state. That's the way this works. But the thing is that this works in parallel. So every cell has 2 neighbors, except for the ends. And this can allow you to propagate changes across this one-dimensional array. And so this is the idea kind of behind modern cellular automata and agent-based models. So this is a finite state machine, and this is similar to the idea of what an automata does over time. So we were looking at the spatial aspect. This is what it does over time. You have these things like this turnstile, and it has a couple of states. It has a locked state and an unlocked state. You put a coin in, it becomes unlocked. You push it, it becomes locked. And there are all these state transitions. And I think you talked about this in NeuroMatch, probably in Markov models, because it's very similar to a Markov model. Well, anyways, we can combine these, and we can think of this as an agent. And so agents have, more generally, agents have a couple of components. So agent-based models are pretty diverse, but they all have these basic 3 components. Each agent has to be some sort of individual unit. So it's a cell, but the cell itself has to have attributes like an internal state and a timekeeping mechanism. So it has to count in time, and it has to have an internal state, and it has to be able to change that state. Each agent has to exist in a world, so it's not good enough just for the agent to exist on its own. It has to interact with its neighbors, and it could be in a grid or in some other type of world. And then they're interactions between agents, and this is the crucial part. They're explicit interactions in terms of rules, or they could be in neighborhoods where, like in the 1D example, you had a cell responding to what its neighbors were doing. Or they could exist in networks. So any cell that's connected to another cell, they're listening to each other and influencing each other. But then we can scale each agent into an agent-based model. So we can take these individual units and form an agent-based model. So we have a bunch of these agents. And those kind of models consist of 3 components. So agent-based models forecast the state of a system. So we might want to build, say, an agent-based model of a city. And we can do that by taking a bunch of agents and putting them, arranging them in a certain way, running the system, and all these agents are doing things, interacting, and they allow us to build forecasts of what a city might look like if you, say, build a big building somewhere. What's going to happen with the agents in that city? Or if you build a freeway, what happens to the agents? We can build scenarios around that. We can also model emergent behaviors. So we can build things that emerge from like a bunch of agents into a collective thing. And so you'll see examples of that later on. Also, we can generalize to the macroscopic scale. So we can generalize from the behavior of individual agents to these large groups of agent behaviors. But before we get into that, I have to distinguish between something called black box and white box modeling. And so we think about agents and we think about automata, and they're basically, we can abstract them to these box and arrows type thing, type relationships. It's, this agent has an effect on this agent has an effect on this agent, and so forth. But the way that we model those boxes, those containers, is important. And so there are a couple ways of doing this. One way is a black box model, where we simply say, this is, we just blindly apply a rule. Maybe it's blindly generating a state, and then it's getting, influenced by its neighbors, but we don't really know what's going on inside. And so when we talk about the brain, a lot of times it is a black box model because we don't really know what's going on inside the brain. I mean, we have some idea, but it's not necessarily clear. You can also build a white box model, and that's a little bit different. A white box model is it's based on what they call first principles. So if we think about the brain again, we might have an agent, and we might actually model the brain a little bit, like we did in the project. We might say, well, there's a feedback loop here that's allowing the agent to take in information, think about it, and then act upon that information with feedback, and maybe feedback from its neighbors, and there's a complex arrangement there inside the brain, and then that generates the rule. So we have those type of first principles. It's still not like, a realistic model of what's going on inside, but we have some principles we can apply to it. And then there's the gray box model, which is a mix of the two. So you can have just a black box model that says, I'm going to model the behavior exactly as it's outputted. I mean, a white box model would be like, I'm going to build a little internal model that says that it's going to do some processing within the agent. I don't know if that's really what's going on, but it's some principle that I think is happening inside the agent. And then the gray box is a combination of the two. So you can actually incorporate brain modeling into agent-based models in this kind of way. But another thing that we have to think about is that, like I said before, you have a bunch of agents and they're acting collectively, and they result in these emergent patterns. So the emergent patterns are like this termite mound. This termite mound is built from a bunch of termites, and they build these huge towers. I mean, they're, several feet tall, and you can think of the size of a termite. You can see how vast that is to a termite, that scale. But these are collective structures. The termites, interact with one another, and they work in social communities, and they build these things. Now, the problem is that we can observe those things being built, but it's almost impossible to do the inverse problem, and that is it's almost impossible to go backwards and figure out all the interactions and causal mechanisms that produce the structure. So these structures are just like interactions that happen over time, But if you were to go back and try to reverse engineer it, it would be hard because the interactions are, you can have many different types of interactions leading to the same structure. And B, there's no guarantee that if you do the same thing again, that it'll lead to this termite mound. So this has been observed by people working on what they call ant colony optimization. And this ant colony here. Oh, I exited my presentation. So people have taken inspiration from ant colonies, and they've used a type of programming optimization that focuses on ants as agents and their interactions in these groups. And so this is an interesting area. It isn't directly agent-based modeling, but it's very similar. Actually, ant colony optimization is agent-based modeling, but it's a different version of it than what maybe a lot of people have seen before. So there are three people we have to talk about then, historically, as well as von Neumann, and that's Ashby, who's on the left here, Simon, who's up in the upper right, and Schelling, who's down here. And all these people have kind of contributed to agent-based modeling in their own way. Ashby wrote a paper in 1958. And this was on his requisite variety idea. And he argued that systems are too heterogeneous and information-laden for what they call reductionist approaches. So he argued that you need to model systems, you need to have some sort of methodology that allows you to observe these emergent effects. And so agent-based modeling is an attempt at that. Simon, who wrote a lot of things, but this paper, Architecture of Complexity, he observed, and I'm just paraphrasing here, hierarchy is a universal feature of complex systems. So, you have these individual agents, but they exist in a sort of hierarchical system where you have these emergent structures that are, above the individual agents, and you have things underneath the agents that are influencing them. And so it's a hierarchy, but you can use the same type of model to model a wide variety of things. And then finally, Schelling, he was a sociologist, he wrote this paper, Dynamic Models of Segregation. And he showed that you can get segregation of agents from a random initial condition. So you can get agents with different states. They can segregate over time and spatially segregate themselves, given a random initial condition and some rules. And we'll talk about that in a minute. So this is the Schelling segregation model. And he wrote a book in 1978, Micromotives and Macro Behaviors. This is a follow-up on the paper that he wrote in the 60s. And his observation was that if you have two groups, red and blue, you can see on the right this grid, and they have a degree of preference for homophily, meaning they want to have a neighbor of the same group, then the cells will change their place of residence to be near a cell of the same color over time. So every time step, they start to want to be near a neighbor of like state. And so over time, there's a self-segregation of the cells, and they go from like a totally random condition where it's like almost like white noise on a television screen to this sort of these sort of clumps and continuous areas of one color or another. And so he observed this thing happening over time, and he says this is an outcome of people having just a simple rule, preference rule, and you can observe this emerge over time. But the important thing about that emergence is that there are these tipping points. So you can have, like, say, a local preference for things, but it doesn't necessarily lead to these patterns. What you need is a tipping point, and that's a transition from a random assortment of particles to these patches. And so I know maybe people have heard of the tipping point. This actually goes all the way back to Schelling, and the tipping point is maybe it's qualitative, but we'll see in a bit that it might be a little bit more quantitative as well. But you can also model consensus with cellular automata. So you can model segregation, which has sociological applications, but you can also model consensus. And so consensus is where a bunch of agents. Well, I guess segregation is sort of a consensus amongst different groups of agents, but consensus is where there's this, they build like cooperation and things like that. And so for a critical value of X, the model will undergo a phase transition or a change in state. So from that random condition to like a clumpy condition where they're coherent groups. Like the segregation model, a consensus model also shows a tipping point. But unlike a segregation model, there you can observe this phase transition that results in favorable conditions for cooperation. And so in this paper, in robotics and autonomous systems, they observe that this X, which drives this emergence and tipping point, is what they call an order parameter. This is similar to Langton's parameter. And it's basically the idea that there has to be a lot of background activity in order to trigger this tipping point. And so the cells have to be, changing their state consistently or sampling each state consistently before they transition to this new state. And so what I've done here is I've shown that you can put some qualitative meat on the bones of this idea of phase transitions and tipping points. But cellular automata are another example of sort of an agent-based model. And the reason I bring up cellular automata again is because they have these rules. They have these macro rules that govern the entire system. So this is a collection of agents, and they evolve according to this rule. Like I said before, you can have these nondescript rules that are just observe what your neighbor does, but you can also have these rules that are numbered that were discovered over the course of the past several decades, where if you have these rules and they get implemented over time, these cells follow the rules, they form these really intricate patterns. And the rule actually leads to different cellular automata that can do certain things. So, for example, this cellular automata has implemented Rule 110. And what the rule does isn't really important, but just suffice it to say it's a distinct rule that's specified to each cell, and they do this in parallel. And this rule leads to a regime that's sort of on the edge of chaos, which means that it's, it can exhibit like rapid shifts in state and some disorder. It's associated with what they call Conway's game of life, and it supposedly supports universal computation. But on the other hand, Rule 30, which is another rule that can be implemented, displays aperiodic chaotic behavior. And what's important about this is that it really does match up with shell patterns that you see in nature. So if you go down the beach and you see a shell pattern, these shell patterns have often formed in a way that's similar to what a cellular automata does. And that rule has been isolated, and we know kind of how that operates. And then the third example would be Rule 184, which actually is very different from the other two rules, but it actually operates as a rule, and it operates in parallel with all these agents. And in this case, it can actually solve what they call the majority problem. It can model one-dimensional traffic flow and the deposition of materials onto a surface. So these cellular automata mimic things that we see in nature. And so this is the universal constructor. This is von Neumann's machine that, where he takes an agent and he makes it really complex. He adds in like all these different program functions, and then he evolves them, and then they generate this complexity. So these are just independent agents. These are similar to modern artificial organisms, but this is an example of an agent having a very complex inner state. And cellular automata are also spatially distinct. So like agent-based models, cellular automata do things that are spatially explicit. You can model a cellular automata in a number of ways. You can use a regular grid, a hexagonal grid, a Voronoi grid, which is a different type of way of distinguishing shapes, and then a 3D grid, which is a three-dimensional array. And so the spatialization allows you to represent fluxes and changes that are otherwise hard to visualize. And so you can see the effects of spatialization here on different behaviors. So, if you have loneliness, the neighbors are not doing anything, so this cell dies out. Overcrowding results in cells taking on different states depending on what its neighbors are doing. So these are all cellular automata neighborhoods that are where there's a cell that's behaving within that neighborhood, and it's changing the state of its neighbor cells are changing its state depending on its neighbors and so forth. And this is being shown over time. But the important thing here to see is that there's a spatial sort of aspect to this, where things can propagate in space, or they can die out in space, or they can be sort of restricted in space. And that's really the important thing to remember, is that agent-based models are built on the cellular automata idea of spatiality and things unfolding in space. So this is, well, we turn kind of agent-based models more. And agent-based models have been used in a number of contexts, and we'll talk about those now. So the first one is that they've been used to model morphogenetic systems. And if you're interested in developmental biology, or even if you're not, this is a good review to go look at. And this tells you a lot about how this agent-based models have been applied to biological development. And so morphogenetic systems just means that they're making spatial patterns. They're growing patterns of cells in space. And so in development, we have things like striping. We have embryos that form shapes. They, emerge from this ball of cells into a distinct set of shapes. And this happens in a way that's emergent. We can't really easily describe it using a reductionist method. So we use these agent-based models, and it helps us understand this process. And so you can test different hypotheses about the developmental biology of the embryo, for example, using ABMs. And we can show that these outcomes are developmental-like. So we can look at like I said with the Turing test, we can look at the system and say, this looks plausible. Or we can even measure it quantitatively, and it looks plausible, then we evaluate it thusly. So, this is just one example. Morphogenetic systems are maybe a natural fit to agent-based models. But we can also look at cities. And we can look, this is Will Wright on the right. He was the creator of SimCity, which is this urban simulation, which under the hood here uses a bunch of cellular automata grids. And, you put a building on a space here, and it changes the value of the neighborhood. You develop something, you put a lake, it changes the value of the area around it. So it has this sort of property of, spatiality. It also has things like unexpected events like alien attacks. It's a good way to model a city. It's not necessarily realistic, but we can understand the dynamics of a urban settlement using this kind of method. And there's a book, Self-Organization in the City, by Juval Portugali, which is a book on cities and self-organization, and how self-organization kind of describes the evolution of urban settlements. And so that's another application of agent-based models. But say you want to actually do this on your own, and maybe you're not interested in embryos or cities, and you want to just model agent behavior. So there's a platform called NetLogo, and this is a platform you can download off the web for free. Mm-hmm. And they have in this platform, it's a graphically driven interface, and it has a bunch of different simulations in it. And so it ranges from the typical cellular automata-based models to game theory models, which is what I'm showing you here, to some other models of collective behavior. And so in this case, I'm showing you the in-person iterated prisoner's dilemma. And the prisoner's dilemma, if you know anything about game theory, it's a pretty famous game where you separate two prisoners and you ask them to rat on each other. And if they don't rat on each other, then they both win. But if they one rats on the other, then one of them loses. And there's a complex payoff structure to that. In this case, it's all these agents are doing this in parallel. So all these agents are exhibiting this sort of prisoner's dilemma, and they're not doing the calculation of every agent in their head. They're just doing the calculation of their neighbors. But this is happening in parallel. And so you can see that you can set the payoff for different strategies. and then the average payoff across all the agents is shown in this graph. And so, given your payoff and given this sort of spatial interaction of the agents and this sort of, distributed nature of actually interacting with a subset of your neighbors at any one time, you get these average payoffs. And so I encourage you to play with this platform because it does really give you a sense of power in terms of understanding these sorts of collective behaviors. But we can also combine agent-based models with other things. So we can combine it, say, for example, with reinforcement learning. So we have an agent-based model, and we couple that with a CompNet, which is something that they're using to implement reinforcement learning. And they find that they can use the interaction and reward structure of a reinforcement learning algorithm to contribute to the rules of a cellular or an agent-based model. So this is something they call interdependence learning.
This is deep Q. Is that related to Q learning, or is that just?
Yeah, it's related to Q learning. So they have this Q learning. They're using Q learning, and I didn't get the details out of the paper. This is the paper, if you're interested. But they're using some version of Q learning, and then they're modeling this segregation model, which is a very classic model, as I showed you in agent-based modeling. And they're able to actually get these simple interaction models where you have strategies that have memory. So, the reason you would couple it with reinforcement learning would be to give the agent a memory. Mm-hmm. And you can even use genetic algorithms to refine these results. They mention this in the discussion. You can use a number of different techniques to model this memory and give the agents a little bit more depth. The system is random, heterogeneous, and shows these complex interactions between agents. So you can see there's this segregation parameter, and they look at it over 5,000 iterations. And depending on your parameter values, it varies quite a bit. And so this is one way of combining agent-based models with other types of models. Another one is to look at the evolution of specific questions. So in this case, it's the evolution of cooperation, where they're looking at a bunch of agents that are sort of evolving cooperation from nothing. And so, in this case, this is another paper, Collapse of Cooperation in Evolving Games, where they look at cooperation collapsing amongst a bunch of agents as opposed to emerging. And so in this case, they allow individual payoffs and strategies to evolve in response to selection on heritable mutations. So each agent has a genome. They have, a set of states, and then they mutate those states. So in this case, you have a strategy that consists of a bunch of states, and you can create mutants where the strategy changes. And so this sort of mimics a genome and mutations and the effects of mutations. And they show that the collapse of cooperation results in average payoff declining, despite increasing payoffs for mutual cooperation. So they have this situation where the average payoff declines. They're increasing individual payoffs for mutual cooperation, but there's still a collapse of cooperation overall. Sort of reminiscent of the n-player iterated prisoner's dilemma back here, where you have the same sort of situation, and you can indeed observe this sort of thing. But these agents have a much more limited state than in this other study. So the internal state here is much more complex. Finally, last slide is on crowd dynamics. And so I don't know if any of you have heard of crowd dynamics, but there's this, I don't know if you've ever seen the second Matrix movie, but the scene where the 100 Agent Smiths, that's basically crowd dynamics that they've implemented in a computer. And people have been studying this since the 1990s. So Dirk Kelving published a book, Quantitative Sociodynamics. And in it, they basically study crowd dynamics. So you have a bunch of people who are like agents in an agent-based model. They're not on a grid anymore, but they're kind of running around in space, and they're interacting. They're interacting with each other, but they're also interacting with objects. So in this case, there's a wall, and they run into this wall and pile up. It's not the most intelligent crowd, but they're doing this to see what happens with crowds. And I think it's really almost kind of comical if you're. But yeah,
out of the room or something.
Yeah, I think there's a crowd dynamic simulation where they're trying to figure out how to get people out of a room. Because if there's like a fire and they have to evacuate the room in a ballroom or something, they have to funnel people out. Well, they're trying to figure out the best way to do that. But this is like just a kind of a failed experiment in that, I guess. But yeah, they do this. They model crowds to see how they behave. And it's useful, but it's also can be somewhat comical. But anyways, this whole thing revolves around agents. They have some internal state, and they exist in these crowds, and the crowds do things, and the crowds actually have dynamics that are greater than the individual. So an individual might run in a certain direction, might keep their distance from other people, but they might still end up doing something like this. And the reason is because the internal state of the agent is modeled as this motion, which is composed of two components. Force, which is this internal motivation to move at a certain speed, and a response or reaction, which is interactions with other pedestrians and boundaries. So you're just basically observing other pedestrians superficially. You're not really modeling their mind, you're just watching where they are. You're watching out for boundaries, and then you have this motivation to move forward at a certain speed. There's no feedback with respect to like, that's a boundary, or that's maybe a bar, I'm going to hit it. But you can see that you can model motion much more in a much more complex manner if you were to, be so inclined, and it would change his crowd dynamic significantly. So that's, I think, all I had to say on agent-based modeling. I wanted to put together something somewhat eclectic, just to give people a sampling of the area.
Yeah, and for people who, which I think is, people who are watching this by any chance, or everybody who's currently here in the lab besides me right now, like this is, there's a lot of things tied into what we've been doing in the lab here, and I don't know if any of it was explicitly done in an agent-based. Like it wasn't done in NetLogo, but that's one of the things that obviously I've been looking at. This presentation is really cool in thinking about things with the lab, but also like NetLogo was mentioned itself, and even like there's the Santa Fe Institute, which is one of the major complexity science institutions in the world, as far as I know. They do something called Complexity Explorer. And they have a course called like Introduction to Agent-Based Modeling, which is featured in NetLogo, or features NetLogo as the programming language and platform for it. And I feel like this is actually a really great complement to the material in that course. I didn't finish the course yet, but I started it prior to the summer, basically. So it's really, there's a lot of things. If you're at all interested in this, I would say bring it up in the Slack. Because this applies to some of our past projects. Just as a reminder, this totally applies to the NeuroMatch complexity feedback as well. Maybe not directly in that specific data set, I don't know, but like there's agent-based modeling implications for that project for sure. So that's my opening volley about that.
Okay, well, I think we're out of time for now. I'd like to, if people have comments, they can leave them in Slack. And then I'll make the slides available, and I'll make this recording available on YouTube, and maybe we'll get some conversation about this. I just hope that people found it useful, and yeah, so I think that's enough for one meeting.
Yeah.
We'll talk more next week. We'll talk about the project more from NeuroMatch. We'll probably talk about other things as well. If anyone wants to bring up any topics that they're interested in or things that they want to discuss, let me know.
Yeah, the lab meetings is sort of, there's obviously a lab agenda, but for people who are new or interested in specific topics, like I know Suniti wasn't here today, but she's mentioned a lot of things about aging and her own project in NeuroMatch and her own interests. So we may hear more from her next time about stuff, or the lab has really been focused on NeuroMatch for the month because we're all involved in it in one way or another. And now we're returning to kind of regularly scheduled programming, so there's some even more opportunity to sort of be involved, or if you see a project that you're interested in or an idea to flesh it out, just encourage you to bring that up to me, to Bradley in the Slack, wherever you want to do it. But yeah.
Yes, this is a good opportunity to like kind of reflect on NeuroMatch and kind of follow up on some of those things that you might be found interesting. So
that's it. Congratulations on making it through. Everybody who's remaining, and thank you, Bradley, for being a mentor for the group, and obviously, but it was an experience, and I'm ready to get more rest. So yeah.
All right, everyone, take care.
Bye-bye.
Bye.
Take care. Bye bye.
Yep, take care. Bye.